buckle up, everyone, because we're diving into a world where optical systems can learn and adapt at the speed of light.
Yeah, the world of photonic neural networks,
Exactly. We're talking about merging the power of photonics with artificial neural networks.
essentially giving our optical systems a serious brain boost using light instead of electronics.
And a roadmap for this deep dive is the paper Artificial Neural Networks for Photonic Applications.
Published just a few months ago in August 2024.
Right, and we're going beyond just the theory here
We're getting into how to actually build these photonic neural networks.
because the implications are huge, right? I mean, think about real-time medical image analysis that can detect the tiniest tumors or instantaneous communication across vast distances.
Even the ability to design entirely new materials, all thanks to the speed and efficiency of light.
Okay, so neural networks, we know they learn from data to make predictions,
Right.
but why use photonics? Why not stick with just using traditional electronics?
Well, that's a great question, and the answer boils down to the amazing properties of light. First off, speed. Light is the fastest thing out there, meaning these systems can process information at speeds that make electronics look like they're frozen in time.
So speed is a game changer.
Absolutely, and that's crucial for things like real-time communication and processing massive amounts of data.
So speed's a big one, but I'm guessing there's more to it than just that, right?
Oh, absolutely. Light beams, unlike electrons, they don't interfere with each other.
Ah, okay.
So we can have a ton of processing happening all at the same time.
Simultaneously.
Yeah, we call this parallelism. It's like having thousands of processors working together in perfect sync.
So we got speed, we got parallelism,
Right.
anything else?
Well, let's not forget about efficiency. Photons don't generate nearly as much heat as electrons do,
Oh,
meaning these systems could potentially be way more energy efficient.
interesting.
You could have incredibly powerful computing systems that don't need these massive cooling systems.
We're talking faster, more powerful, and greener computing. That's a pretty compelling argument for photonics. But I imagine building these systems is not exactly a walk in the park, right?
Yeah, you're right. One of the biggest hurdles is figuring out how to translate these software concepts of neural networks into physical hardware that uses light.
Yeah, I can see how that would be tricky.
It's like trying to build a computer out of light beams instead of wires and transistors.
So where do you even begin with something like that?
Well, one of the key operations in many neural networks is something called matrix multiplication.
Okay.
It's a fundamental mathematical operation that's essential for neural networks to process and make sense of all the data they receive.
Hold on, matrix multiplication. I'm getting some serious flashbacks to high school algebra here.
Yeah.
Can you break that down for us a bit?
Think of it this way. You have a grid of numbers, like a spreadsheet,
Okay.
and you need to multiply it by another set of numbers.
Right.
This operation is what allows networks to analyze and make sense of the data they're being fed.
Okay, so how in the world do you do that with light?
Well, researchers are coming up with some incredibly clever ways.
Okay.
One approach uses something called spatial diffraction.
Okay.
It's kind of like, imagine shining a flashlight through a stencil.
Okay.
The pattern that you get on the wall, that's like the result of a matrix multiplication.
Okay.
But instead of a flashlight, we're using carefully designed light beams.
Right.
And instead of a stencil, we're using these specially engineered optical components.
Oh, that's a great analogy. So by manipulating these light beams,
Right.
you can actually perform those complex mathematical operations.
Exactly.
What other techniques are being explored out there?
Another method uses these networks of Mach-Zehnder interferometers.
Say that again?
Mach-Zehnder interferometers.
Mach-Zehnder interferometers.
Yeah, these are tiny devices that split and recombine light beams to manipulate the signal,
Okay.
kind of like microscopic traffic controllers for photons.
Interesting.
And by carefully adjusting the paths of those light beams, we can perform the matrix multiplication optically.
So we're using the properties of light itself to do computation.
Exactly.
That's incredible. But matrix multiplication is just one part of a neural network, right? What about all the other complexities that make these systems so powerful?
You're absolutely right. Neural networks are incredibly complex with layers upon layers of interconnected nodes
Right.
and these intricate activation functions that introduce what we call nonlinearity,
Okay.
which essentially allows them to learn these really complex patterns.
So how do you translate that complexity into the world of photonics?
Well, that's where photonic activation functions come in.
Oh,
We need to figure out ways to introduce that nonlinearity into the optical system itself.
I see.
And there are a couple of main approaches for doing this.
Okay, what are the options?
One approach is what we call fully analog,
Okay,
meaning we use the intensity of the light itself as the signal.
got it.
Think of it like turning a dimmer switch up or down, you know? The brighter the light, the stronger the signal.
That sounds pretty straightforward. What about the other
Right.
approach?
The other approach is what we call hybrid,
Okay.
which combines the speed of optics with some digital processing.
Interesting.
This approach often gives us more flexibility and control, allowing us to fine-tune that non-linearity of the system.
So I see the appeal of both approaches,
Yeah.
but I'm guessing there are some trade-offs involved, right?
You're absolutely right. Fully analog systems can be blazingly fast,
Yeah.
but they can be harder to control precisely.
Yeah.
Hybrid systems offer that extra control,
Right.
but might sacrifice some of the speed advantages that we get with pure photonics.
So it's a balancing act.
Yeah, finding that sweet spot between speed, control, and complexity is a major focus of ongoing research.
So you need to find the right combination of optical and digital components to really get the desired performance. This is all very impressive, but I can't help but think about the practicality of all this.
And that's a crucial point. Building a small-scale photonic neural network in a lab is one thing,
Right.
but how do we actually make these systems practical for real-world use?
Right, because we can't exactly have room-sized optical computers in our homes and offices.
Exactly. And that's honestly one of the biggest challenges in this field.
Yeah.
How do we make these systems smaller, more efficient, and ultimately more affordable?
So the challenge is to shrink these powerful optical systems down to a manageable size without sacrificing performance.
Exactly.
That sounds like a pretty tall order.
It is. And that's where the concept of complexity really comes into play. Building a powerful photonic neural network is one thing.
Right.
But if it's too complex,
Yeah.
it becomes incredibly difficult and expensive to actually manufacture.
Right.
Imagine trying to build a computer chip,
Okay.
but instead of transistors, you're working with these tiny, delicate optical components.
It's like trying to fit an entire city's infrastructure onto a postage stamp.
Exactly.
So how do researchers tackle this challenge of complexity?
Well, one promising approach is to take inspiration from nature.
Okay.
Just like biological neural networks have evolved over millions of years to be incredibly efficient. Right.
Researchers are looking at ways to mimic those efficiencies in photonic systems.
So it's about finding those elegant solutions that achieve maximum performance, but with minimal complexity.
Exactly. It's about streamlining the design, getting rid of unnecessary components,
Okay.
and finding clever ways to multiplex signals.
Okay, like what?
Well, one technique is wavelength division multiplexing.
Oh.
It's like sending multiple messages over the same fiber optic cable,
Right.
but using different colors of light for each message.
Oh, that's fascinating. So by borrowing these design principles from nature
Right?
and leveraging these advanced optical techniques,
Yeah,
researchers are finding ways to make these complex systems more manageable.
exactly.
Speaking of different types of neural networks, I know we've talked about dense layers and convolutional neural networks and recurrent neural networks.
Right.
Are there any other types that are particularly well suited for photonics?
Yeah, there are a few others that deserve a mention.
Okay.
One that stands out is what we call the Echo State Network, or ESN. ESN.
Okay. What's unique about ESNs is that only one part of the network actually needs to be trained.
Really?
Yeah, making them incredibly fast.
Wow. How does that work?
It's all about using the inherent properties of light to our advantage.
Okay.
Imagine a fiber optic cable that's looped back on itself.
Right.
This loop acts as a kind of reservoir for remembering patterns.
Okay.
The ESN feeds information into this reservoir,
Right.
and then only the output layer of the network needs to be trained to interpret the results.
So you're essentially using the physical properties of the optical system itself to simplify that training process.
Exactly. This makes ESNs incredibly efficient for certain tasks,
Okay.
especially those involving time series data like the signals traveling through a fiber optic cable.
That's ESNS. Any others?
Another interesting type is what we call the attention layer.
Attention layer. Okay.
These layers help the network focus on the most important data within a signal,
Okay.
kind of like a spotlight that can highlight the key information.
That sounds incredibly useful, especially when you're dealing with the massive amounts of data that these optical systems can generate.
Absolutely. Attention layers are all about efficiency.
Right.
They help the network prioritize what to focus on,
Okay.
which can dramatically improve accuracy and reduce processing time.
So it's all about cutting through the noise and focusing on what really matters.
Exactly.
Okay, so we've got attention layers. What else?
Then there are transformers,
Transformers.
which are kind of like the masterminds of understanding these complex relationships in data.
Okay.
They use attention mechanisms to analyze how different parts of a signal relate to each other.
So attention layers help filter out the noise,
Right.
and then transformers help connect the dots.
That's a great way to put it.
Okay, so attention layers, transformers.
And then we have residual neural networks, or ResNets,
Was next.
which are all about efficiency.
Okay,
They create shortcuts for information to flow through the network,
got it.
making deep networks much faster to train.
So ResNets are like the express lanes of the neural network world.
Exactly. And what's really cool is that you can actually build ResNets optically,
Oh, wow.
using mirrors and beam splitters to create those information shortcuts.
It's amazing how researchers are finding ways to translate these like abstract software concepts
Yeah.
into actual physical optical systems.
Yeah, it's really fascinating.
We've covered a lot of ground here, from
Mhm.
the fundamental advantages of photonics to the challenges of complexity to all these different types of neural networks
Right.
that are well suited for optical implementation.
Yeah,
It's clear that this is a rapidly evolving field with just enormous potential.
absolutely. And, we've made significant progress,
Yeah.
but we're still really in the early stages of this technological revolution.
Right.
There's so much more to discover and so many challenges yet to be overcome.
Speaking of challenges, I think one of the biggest hurdles for any new technology is scalability.
Yeah,
It's one thing to build a proof of concept in a lab,
right.
but quite another to mass produce these systems for widespread use.
Absolutely.
So what are some of the key considerations when it comes to scaling up photonic neural networks?
Well, scalability is definitely a key concern. We need to find ways to manufacture these complex optical systems reliably and cost effectively.
Right.
One promising approach is to leverage existing semiconductor manufacturing technologies.
So it's about adapting the processes we already use to make computer chips to create these photonic components.
Exactly. Silicon photonics is a particularly promising area of research.
Okay.
By using silicon, which is already the backbone of the microelectronics industry,
Right.
we can take advantage of those economies of scale
Yeah.
and the manufacturing expertise that's already out there.
That makes a lot of sense. It's like repurposing those factories that make our smartphones to start churning out these photonic chips.
Exactly. It's about finding those synergies between existing technologies and these emerging fields.
Okay.
And, it's not just about the manufacturing process. We also need to develop new materials and fabrication techniques that are specifically tailored for photonic applications.
So it's a multi-pronged approach.
Right.
We need to find new ways to build these systems,
Yeah.
new materials to build them with,
Right.
and new manufacturing processes to scale up production.
You got it. It's this fascinating convergence of engineering, material science, and computer science.
But let's not forget the software side of things.
Oh, absolutely.
We need to develop new algorithms and architectures
Right.
that are specifically optimized for the unique properties of these photonic systems.
It's not just about building the hardware, it's also about developing the software tools and design principles
Right.
that will allow us to really harness the full potential of this technology.
So it's a holistic challenge that requires expertise from multiple disciplines.
Yeah.
It's like assembling a dream team of engineers, scientists, and programmers to really push the boundaries of what's possible.
That's a great analogy. And what's really exciting is that we're seeing this incredible collaboration and cross-pollination of ideas across all these different fields.
It's like witnessing the birth of a new technological era,
It really is.
where light and intelligence converge to
Uh-huh.
create something truly remarkable.
And one of the key things that researchers are really focusing on right now is finding that right balance between the analog nature of optics and the digital world of computing.
That's an interesting point. I mean, we've talked about how light has these incredible analog properties,
Right.
but our current computing infrastructure is largely digital.
Right.
So how do you bridge that gap?
Well, that's where those hybrid approaches we talked about earlier come in.
Yeah.
By combining optical processing with some digital components,
Right.
we can really leverage the best of both worlds.
So it's not about choosing one over the other.
Exactly.
It's about finding the right synergy between the two.
Exactly. And this is where things get really interesting. By carefully integrating these two worlds, we can unlock entirely new computational paradigms that could lead to breakthroughs in artificial intelligence, machine learning, and beyond.
It really does sound like we're on the cusp of a computing revolution.
It is.
But let's shift gears for a moment.
Okay.
Talk about some real-world applications.
Sure.
Where are we likely to see the impact of these photonic neural networks, in the near future?
Well, one area where they're already making waves is in optical communications.
Okay.
The ability to process signals at the speed of light, it's a game changer for high-speed data transmission.
So are you saying we could have even faster internet?
It's not just about speed, though.
Okay.
Photonic neural networks can also improve the quality and security of that data transmission.
Interesting.
Imagine a world where your data packets are analyzed and corrected in real time as they travel across the globe,
Wow.
eliminating errors and ensuring data integrity.
That sounds like a dream come true for anyone who's ever experienced a laggy video call or a dropped connection. What about security? How can photonic neural networks make our data more secure?
Well, security is another area where photonics really shines.
Okay.
Imagine encryption algorithms that operate at the speed of light,
Oh,
making it virtually impossible for hackers to intercept or decipher sensitive information.
it's like having an unbreakable digital vault for your data.
Exactly.
Okay, so faster, more reliable, and more secure internet. Sign me up.
Right.
What other fields are ripe for disruption by these photonic neural networks?
Well, medical imaging is another area with huge potential.
Okay.
Think about real-time analysis of medical images, enabling doctors to spot even the tiniest abnormalities
Right.
with incredible accuracy.
So we're talking earlier diagnoses, more targeted treatments, and potentially even preventing diseases before they even take hold.
Exactly.
That's incredible. It sounds like something out of a sci-fi movie,
I know, it's really amazing.
but it's becoming a reality right before our eyes.
It is.
Are there other applications, beyond healthcare that you're particularly excited about?
Oh, absolutely. Environmental monitoring is a field that stands to benefit greatly from photonic neural networks.
Okay, how so?
Imagine a network of ultra-sensitive sensors deployed all across the globe, constantly monitoring air and water quality,
Okay.
detecting pollution levels, and providing real-time data on the health of our planet.
It's like giving our planet a nervous system, allowing us to sense and respond to environmental changes
Yeah,
with this unprecedented speed and precision.
it's really remarkable.
This is all incredibly inspiring, but
Huh.
I have to ask, what's the biggest takeaway you want our listeners to walk away with? What's the one thing you hope they'll remember from this deep dive?
I think the most important message is that we're at the very beginning of a new era in computing.
Okay.
For decades, we've relied on electronics to power our digital world,
Right.
but we're hitting the limits of what electronics can do.
Right.
Photonics offers this fundamentally different way to process information,
Yeah.
one that's faster, more efficient, and potentially far more powerful than anything we've seen before.
So it's not just an upgrade.
No.
It's a complete paradigm shift.
Exactly. And while there are certainly challenges ahead, the possibilities are truly limitless.
Right.
This technology has the power to completely reshape our world
Yeah.
in ways we can only begin to imagine.
Absolutely.
From revolutionizing healthcare and communication to safeguarding our environment
Right.
and unlocking new frontiers in artificial intelligence.
It's amazing.
The future is bright and it's powered by light.
This has been an incredible journey.
It has.
We've gone from the basic principles of neural networks to the mind-blowing potential of this photonic computing.
Yeah.
We've explored the challenges, the breakthroughs, and those tantalizing possibilities that lie ahead.
It's exciting.
It's clear that we're on the verge of something truly transformative.
We are.
And what excites me most is that we've only just scratched the surface.
I agree.
As research in this field continues to accelerate, I have no doubt that we'll see even more groundbreaking discoveries and applications in the years to come. So to our listeners, keep your eyes on the light.
Right?
The future is photonics. That's it for our deep dive into the world of photonic neural networks.
It's been a pleasure.
We hope you've enjoyed the journey, and we'll catch you on our next adventure into the depths of knowledge.